Good afternoon, everyone, and welcome to the joint EOL Cyprus seminar. Cyprus is the new ASP Community Postdoctoral Research in Earth System Science seminar series. I am new to this series. I'm Sarah Woods from EOL, and on behalf of EOL in Cyprus, I'm very pleased to introduce Dr. Ana del Moral Mendez for this joint hybrid seminar. Ana is an ASP postdoctoral fellow at EOL and RAL, and also visited NCAR previously under the ASP Graduate Visitor Program. She received her PhD from the University of Barcelona, where she worked toward improving the nowcasting of severe weather in Catalonia. Her research focuses on improving the knowledge of severe storms through observations and retrieving better nowcasting products for the operational community to help in decision-making processes and early warning systems. Since 2021, she has also been co-leading the Academia Ambassadors Group for the Committee for Hispanic and Latinx Advancement of the American Meteorological Society. Please join me in welcoming Dr. Ana del Moral Mendez for her seminar titled Towards Improved Short-Term Forecasting for Lake Victoria Basin, Exploring Highway Field Campaign Data. And for those of you watching online, please feel free to put your questions in the Slido box at the bottom of your screen.
Thank you for coming. My name is Ana del Moral, as Sarah introduced me before. I'm an ASP postdoc fellow. I'm recently starting my second year of my postdoctoral appointment. And I'm here today presenting the work that I've been doing these past years toward improving the short-term forecasting for Lake Victoria Basin. We've been doing that exploring the highway field campaign data, which I'm going to introduce a little bit after this presentation. And I need to thank Jim Wilson, Rita Roberts, and Tammy Wegworth because they're my advisors, and this is a joint effort and collaboration all together. So first of all, let's travel a bit, especially for those who are here in NCAR today. This is NCAR Foothills Lab. And for this presentation, we need to go all the way across the globe to Lake Victoria in Africa. This is a great lake in this region. And to state a little bit more about Lake Victoria, it's the largest fresh body in Africa. It's, for those who are in the US, the second biggest lake in the world after Lake Superior. You can see, oh, just let me get the pointer. And I don't see now my pointer. Oh, great. So as you can see in here, in this tiny square in these infographics, it's in the equatorial zone, and it supports the life of more than 5 million people that lives around the lake and also in the small islands inside the lake. It's estimated that there is more than 217,000 fishermen going out every day, and because it's a prosperous region for the fishery industry and also the agriculture. However, if we just go quickly into Google search, we can see that in the late years, there's been a lot of boat accidents. And usually these boat accidents happen to have also like a lot of fatalities. And these boat accidents happen usually because of severe weather that produce large waves on the lake, and then this capsize the vessels, and then people die, especially the fishermen who are out there working overnight. But not just that, also there's been an increase in frequency in the events that affect also the surrounding areas of the lake, for especially like high impact weather events such as flash flooding or severe hailstorms that also causes a lot of economical damages and also deaths, unfortunately, to this population around the lake. So it's estimated that severe weather is a major threat for Lake Victoria Basin, costing around 1,000 deaths per year, which is a really high toll on fatalities. So you might remember from the last World Meteorological Day, this past March in 2022, the main motive was the early warning and early action. And why was that the main motive? Well, the State of the Climate 2021 report stated that extreme weather events led to hundreds of billions of dollars of economic losses and a high toll on loss of human lives. And also the IPCC report stated that early warnings and disaster risk management are an essential adaptation tool to face these high impact weather events. However, we still have a main problem, and there's a major gap in the population worldwide that have access to these early warning systems. And especially in Africa, there's estimated that more than 60% of the population has no access to early warning advice or advisory systems. And there is also estimated that just 26% of the reporting stations in Africa met WMO standards. So to tackle these problems, in 2017, the WMO led a project that just finished recently in 2021, which was called the High Impact Weather Lake System Project, or HIWAY. And this project had a main goal to enhance resilience of East African people and reduce the loss of lives and property, increasing the use of weather information. So there was a gap of new tools and information, so we had to put more observations there to actually understand the weather and then help the population. So during this project that, as I mentioned, was run from 2017 to 2021, there was an enhanced operations period, which was kind of like a field project, not fully like we understand a field project, but similar. It was run in 2019. And here in this map, you can see some of the observations that were put together there for this field campaign. So in these orange circles, you can see the upper air stations, one in Loadvar and the other in Nairobi. But as you can see, they're really far away from the lake. So if you want to actually know more about the weather on the lake, maybe that's not really reliable, especially for low-level weather. And then we also had the 3D printed automatic weather station, or 3D PAUS, here from NCAR, which are these yellow triangles. These yellow triangles, the Trans-Hydrometeorological Observatory, or TAMO station, which are these magenta bubbles, the National Meteorological and Hydrological Services automatic weather stations, which are the green squares that we can see. And finally, and what's more important, they put together 3 polarimetric radars in the lake and surrounding the lake areas. One was placed in Entebbe, a C-band polarimetric radar in Entebbe, which is actually covering half of the lake, the northern shore, and being used as a surveillance tool for especially the airport. Another one in Kigali in Rwanda. Unfortunately, we don't have the data from this radar, so we couldn't work with that radar. And the third one in Mwanza, which is actually an S-band radar, that covers mostly the entire lake, and it's been the main tool in this research. And I'm going to talk a little bit more about this radar in a minute. One of the biggest HIWAY outcomes was these impact-based forecasting charts. These were maps that were released twice a day. And it was important because it was a joint effort between the different countries surrounding the lake, Kenya, Uganda, and Tanzania, that were in charge of producing these forecasts, especially using infographics to get to know to allow the community, especially the broadcasters or radio broadcasters, to have a easy and understandable information that they could translate into their local languages to their communities. So I want you to bear in mind one of the columns in here, and I'm highlighting here how this chart was divided, the forecast. You could see that it was divided in 4 time slots, morning, afternoon, night before midnight, and night after midnight. And I want you to keep that in mind because I'm going to be using this classification throughout this entire presentation. So it's important to focus on that. Also, I want you also to remember a little bit this map and these sectors, and especially because this was also how the lake was divided for the different countries that were forecasting this weather for the lake, and how they were dividing the lake in different sectors in order to release their forecast twice daily. So also my analysis has been based on these sectors that are operationally used. So, as I mentioned, The S-band radar in Mwanza has been the main tool that I've been using for this year of project so far. This is an S-band radar, and it's co-located in this hill in the southern shore of the Lake Victoria, so it's pretty well located to overlook the entire lake and have a good view of the weather happening there. And also, I repeat, it's an S-band, so we have a full coverage of the lake. And this is also a picture of Benedicto Gatole, which is one of the engineers working at that station, and with displaying the weather, the radar and the images that of the weather that was happening on the lake. A little bit more about this radar, and I'm not going to go into a lot of detail, but just important things that we need to understand for this presentation is that it's a S-band radar that it's run in dual pulse repetition frequency. And for those who are not familiar with radar operations, basically that means that we have two different modes of scanning. So we have two different ranges on which the radar can see the weather. Also two different maximum velocities that we can resolve. So with those two ranges, we have a high frequency one range, which would cover 150 kilometers around the radar, and then the low PRF range would be 360 kilometers, which, as I mentioned, covers the entire lake and a little bit farther south of the lake. It's a polarimetric radar, so we have further information, not just reflectivity and velocity. So there's going to be enhanced information to use with this radar, and it retrieves a volume every 10 minutes. So now that I've gone through a little bit of highway and the data, what am I presenting today? Well, first, I'm going to be dividing this talk in 3 main blocks, so because there's a lot of material and I want you to follow the story with me. So first, I'm going to present the identification of the main convective modes over the Lake Victoria and the daily cycle of the convection over lake, and then what are the main summary results that we've found with that. The second block is focused on the identification of key parameters describing the convective environment conducive to the different modes that we've previously found in the first block. And the third block would be based on the analysis of a case study with radar polarimetric information. So we're using radar and other tools to describe the storms and how the nowcasting could be improved in Lake Victoria. So with that being said, this is the first block, identification of the main convective modes, and let's jump into that. So how do we study these convective modes over Lake Victoria? Well, we've used classification type, but for that, what we use is a radar-based identification and tracking algorithm. This is called the Thunderstorm Identification, Tracking, Analysis, and Nowcasting Algorithm, or TITAN. This open source software, it was developed here at NCAR, and what this makes is allows us to identify and track storms in radar volume. So you can get on time information of the daily cycle, of the evolution of these storms, and those parameters. What we've done with that is to classify all the storms that were happening during this field project into 6 different types of complexes. And this was done based on morphological information, such as the major axis of the ellipse that is projected from those storms, the ratio between the major and minor axis, and the maximum reflectivity. And with that, what we get is these 6 different modes that we classified here, from multi-cell unorganized up to upscale linear, representing from less organization mode to a maximum organization mode. Once we had that classification, we defined our complex, and with that definition of complex, I'm going to just explain a little bit more in a minute. But as we define our complex as the maximum organization in the operational time slot. What does that mean? If we have a storm or we have different storms that are inside a complex, and what a complex means is like a group of different cycles or evolutions in different storms. So storms can be isolated, or can be splitting or merging or interacting with the neighbors. So all the single storms will form one single complex. And the maximum organization means that we divided our storms in time slots, in those morning, afternoon, night before midnight, and night after midnight that I mentioned before. And we gave the maximum organization within that time slot. So if we had isolated in morning, would be isolated in morning. But if that evolved into upscale linear in the afternoon, it would have two levels, isolated and upscale linear. And then our analysis was stratified depending on the time of the day, the operational time slots, the number of total levels defined in the complex, defining if it is short or long, depending if it happens in one time slot or more than one, the lake sectors, and we also did this analysis in two different wet seasons. The first runs from March to May, and the second from October, December. So as I mentioned before, this is how a complex is defined. So we would have these different colors define different storms, and these different storms would have different identifiers. One entire complex would be defined by several storms, and each time slot would have a maximum representation for this complex. So in this case, we would have an isolated because both are isolated. The second case, upscale linear, because the maximum is an upscale, and so on. So let's jump into the results for the first stage. And this is a big map that I need to go a little bit over it and explains what I'm showing here. So this is just a representation of, so we will have here different Lake Victoria maps from 6 a.m. Eastern African time. So this is local time, 6 a.m. up to 5 a.m. local time. So it runs for 24 hours. And what we see here is 2D density plot representation of the centroids of this complex that we found. So each tiny dot that we see here are centroids, so the location of the maximum level that we find for one complex. You will see that the colors, the red color is probably the same in all the maps. It's everything because it's normalized to 1, so that's the color. You don't really need to focus on the color. Focus also in this number in here that represents the frequency of events. So this is what I'm going to talk about now. And we've done that, this is important, we've done that for the isolated case because we found that this is the mode that was more representative for the lake. So we have more events of that, and that would represent better our cycle over the lake. So first of all, what I need you to focus on is in this first maximum. This first maximum we have running from 10 p.m. to 3 a.m. in the morning, and we see that the storms are concentrated in the northeastern sector of the lake, running towards the center of the lake, so getting this eastern southwestern flow. Then we have another maximum from 4 a.m. in the morning to 11 a.m. in the morning, where we can see that then the storms are happening in the center of the lake and then moving toward the southwestern shore. And then finally we can focus, well, we can see that there's a minimum happening in the central hours of the day in the afternoon. So what we see here is the convection is happening during the night. So there's nothing happening over the day on the lake. Well, nothing, almost nothing. So with that, what we can define for now is like, well, we had this operational forecast release for morning, afternoon, night before midnight, night after midnight, but let's put some hours into this. So what we define here is our times that are currently involved in those time slots, so we can give further information for the forecasters later, and also to help us properly do the analysis for further studies. So now, from now on, afternoon will be defined from 12 p.m. to 6 p.m. local time. Night before midnight will be defined from 6 p.m. to 12 a.m., night after midnight, 12 a.m. to 6 a.m., and morning, 6 a.m. to 12 p.m. in the morning. So now every time that I talk about these time slots, I'm referring to those times. Another part of this sector of the diurnal cycle on the lake is now that we have the times and we have mostly the diurnal cycle, like on how storms are moving on the lake, let's see what happens with these modes that we represented and where are they appearing. So first I want you to to focus on this map because I need to explain a little bit more in detail on what is this map representing. You would see this map, it's the Lake Victoria, the lines are the sectors again. We have the 4 time slots and from afternoon to morning. And in here I'm just showing the shore complexes. This means that I'm working with complexes that are just happening from start to ending in one of the time slots. And you would see that there's different bubbles and different colors. These colors represent the different 6 modes that we defined, from less organization to more organization in green. And then the bubble size would be the count, so the frequency of events for each mode. So now we've defined this. The first thing that I need you to see is that, again, we see this pattern of thunderstorms and these modes happening in the northeastern side of the lake, especially for isolated and multi-unorganized systems. And then as soon as we get into the nighttime and then also early morning, we see that there's more organizations mode happening. So everything moves from northeast of the lake, and then central part of the lake, and then southwestern side of the lake. And then you would see that also these, as I mentioned, these bubbles first, they just appear to be blue, so less organization. And then finally, we can see also the red and the green, so further organization happening in the central and southwestern parts of the lake. So now let's compare the short and the long complexes. As you can see here, the counts are completely different. So maximum counts in the short complexes would be 200 cases, and for the counts, maximum counts in long complexes would be 40. So that means that we do have more complexes that just happen in one time slot, but that doesn't mean that they are short, because some of the time slots have a lot of hours within that. And finally, if we compare the short complexes and long complexes, but focused on the time slot that we have more activity, which would be night after midnight and morning, we can see that there is a main difference happening with long complexes, and it's that then we don't have the isolated, so the blue bubble being the one highlighted in here, will be more multi-unorganized. So we have kind of like cluster of storms happening during night in the central areas of the lake. But also there's smaller difference in between the big bubbles, so the unorganized cases and the organized cases, which would be the green and the red bubbles appearing in here below. So once we have this as an overview and summary of this convective cycle over the lake, we can see that in the afternoon we have mostly minimal weather, and that would affect mostly all of the sectors, but especially Uganda would be minimally affected. The night before midnight would have convection initiation and established convection, and that would be mostly interesting for Kenya and Uganda. The night after midnight would be organized convection and upscale, and that would be mostly for Uganda and Tanzania. And finally, during the morning, would be upscale growth and dissipation, because we have these more organized modes, and would be interesting for Uganda and Tanzania. So now let's jump into this second side of a block of this presentation, which is the identification of the key parameters describing the convective environment, which is conducive to these 6 different modes that we've analyzed previously. And for that, once we had our classification and we had our centroids for the storms, what we did is go to work with upper air soundings. And unfortunately, as I mentioned, the 2 observational soundings are really far away. And we are in a tropical region, so there's not much of a synoptic scale patterns happening there. So we couldn't have a lot of information from those soundings. So what we did is work with the ERA 5 reanalysis. And for this reason, we used 20 pressure levels. We retrieved each sounding from each complex centroid. So we had this map of different centroids that I showed before in the isolated cases that we have for the 6 modes. So for each centroid, we retrieve one sounding. And then we compared that with the Nairobi sounding, just to make sure that the indices that we were getting from these soundings were correct to analyze. And finally, yes, we work with the Sharpie Sharpie packet, from Python to retrieve the instability and convective indices. Just a quick mention that ERA 5 presents slightly warmer and more humid lower atmosphere than Nairobi sounding. that we've selected 12 parameters with a correlation greater than 75. So it's not just random. We did a lot of correlations in between different parameters. And also over the lake, we need to bear in mind that the wind parameters, especially from the first kilometer, are not well resolved. So we'll have higher errors. And for that, we hope that in the future, with more soundings happening and located over the coast, we would have further information to improve this. So with that, as I mentioned, we have 12 parameters, which are listed in here. These are the 12 parameters that we defined that were worth working with and analyzing. And we have 4 time slots, 10 sectors, 2 seasons, 6 convective modes, and 2 types of complexes. And that means that we have 24 charts like this, box plots, which I'm not gonna show today here because that would be really boring. So I've tried to summarize in really clear information for you to get from these box plots, and hopefully I've accomplished what I wanted. So let's do these analyses by time slots and representing the lake. So first, let's focus on the afternoon time slot. And first, it's worth mentioning that for the instability indexes, the lifting condensation level and the level of free convection are lower in season 2. That means that during autumn, those levels are closer to the surface, and probably it's related because we also we'll see greater humidity values. But also we saw that then the energy, let's see, the mixed layer cape and also the downdraft cape that we were analyzing, it's higher in season 1, which would be our spring, although we cannot talk about spring and autumn there. So this is a pattern that we will see in the entire 4 time slots. I'm not going to repeat that, but mostly is that it could indicate that it's easier to get started the convection during autumn because these greater values of moisture. But then once it pop up in spring, they probably tend to develop into deep convection, and so probably could be even more severe. So with the humidity and moisture values, we saw that everything is higher in season 2. This means October to December. So we saw that relative humidity values in mid and low levels are really high. Just to remind that we're working over the lake, so we expect that to be high. And also lapse rate were really, really important. For this time slot in the afternoon, the wind parameters, there was no significance in anything, so no significant in bulk shear. This was taken in the layer 0 to 6 kilometer, or storm relative helicity from 0 to 3 kilometers. And there was a main thing to mention here. It's that the wind flow in the afternoon goes from lake to land breeze, so lake to land. And this is actually different from another time slot, so it's worth also paying attention to these interactions in this and in the breeze in between the lake and the land, on how these are probably like a key feature to take in mind after for the convection happening. So as a result, we would have in this time slot isolated and unorganized thunderstorms with mostly heavy rain. For the night before midnight sectors, we saw again that these values are higher than in the afternoon. So now if the levels, free convection, are higher, but also the instability is getting higher. So the mixed layer cape and also the downdraft cape. For the moisture, we saw that it's lower than the afternoon. So that's probably because we also have the diurnal heating over the lake in the afternoon. So now we don't have that anymore. And there was a special mention here and something to highlight about the multilinear convective mode. It's that it presented a really dry mid-level compared to the other modes. So we have this really moist low level for other modes, but also this dry mid-level for the multilinear. And that could represent then, that could be also a key feature to bear in mind if we probably expect severe wind gusts, or if these thunderstorms are popping up, especially because of the evaporation cooling. So for the wind parameters, we saw that it was higher in season 2. The bulk shear now gets a little bit more important, especially for organization of multi-cell storms. The storm relative velocity also gets a bit more important, so it could be also some circulations in the storms, and there was, like, these two sectors were highlighted within the 4 sectors that were in the analysis. And as I mentioned, this mean flow changed in this part of the day. So now instead of having lake land, we have land lake. So completely changed in the hours. So that's something to bear in mind. So as a result, we would have unorganized or organized storms, especially the linear ones, representing heavy rain, straight line winds, or waterspouts, because now we have more bulk shear and also storm relative velocity. For the night before midnight, there we can see now that there are like 3 main sectors highlighted here that within the 6 that form this analysis. Everything is higher in season 1. This is spring, it's not really spring, but it's March to May. And there's the clear difference between the sectors. This is where we find the higher mixed layer cape and downdraft cape, which could also indicate that those storms that form over the lake at night, where the fishermen out there in the middle of the lake could represent a severe threat for them. For the moisture values, we have that they are higher in season 2. In season 2, which is October to December, but they are steeper, the lapse rates, in season 1. So again, we have this ability to start or initiate this convection during the autumn season, but it could be deeper during season first. And again, we see that for the linear convective systems modes, we have also this mid-layer, dry mid-layer, which could represent in strong winds. For the wind parameters, they are higher in season 2. There's a special difference between the long complexes and the short complexes. So now it's higher for the long complexes with respect to other time slots. And again, we have the storm relative velocity increasing, which could pop up some circulations. And also for the linear organization, we need to highlight that this was related to southern flow, which could indicate that we have this speed shear parallel to the storm track, so it could maintain the linear organization. So we have these storms, linear storms, moving from the eastern side to the western side, and this southern flow happening, and then helping this organization of these upscale linear systems. So that would represent, again, organized linear modes and upscale growth with heavy rain and straight line winds. And finally, for the morning time slot, we have that they are higher in season first, and there's also a huge difference in between organization modes and sectors. These are the 3 main sectors that are more important for this analysis during the morning. Again, we have mixed layer cape aligned with organized and upscale complexes. These are also higher downdraft cape values in isolated cases. For the moisture, we have it's higher in season 2, so again, steeper lapse rate and higher low and mid-level relative humidity, especially for organized, upscale, and long complexes. For the wind parameters, we do have a tiny change in the bulk shear and storm relative velocity because it's a little bit slower, lower than during the night, but still is aligning with the ingredients needed for these long-lasting and upscale growth linear systems. And finally, that would be summarized as upscale and organized systems maintenance, conducive to heavy rain, straight line winds, and water spouts. So I know that this was a lot of info, and I'm just trying to summarize now in just one tiny slide. So what we get with that is that atmospheric instability over the lake is greater during the night than during daytime. So we have also greater thunderstorms and probably deeper thunderstorms happening during the night. That is increasing the hazard over the lake because first we don't have a visual of those storms, but also we have more fishermen happening to work over the lake during nighttime. Season 2, October to December, presents higher moisture. This may favor storm initiation overnight on the lake. Season 1st, which goes March to May, presents higher mixed layer cape and downdraft capes, which may favor stronger updrafts or downdrafts for deep convection. Wind parameters are different between sectors, convective modes, and the day, the time of the day. So that could indicate the important role of the lake-land breeze interaction. So we need to further our studies in that alley. And a special mention to the southwestern and central lake sectors, which are really important for Tanzania and Uganda, because at night they show that mid-level humidity, bulk shear values, and wind indexes align with upscale growth of previous convection already happening in the lake into these big linear systems. And then finally, the last part of this talk is how to analyze, how do we merge the information that we got before and get further information with this polarimetric radar information. And for this, we're doing a case study. And why did I choose this case study is basically because during highway, there's this paper from Kiwanuka Tondo in 2019. And after surveying different communities around the lake and fishermen operating on the lake, they stated that one of the things that were really frightening for them when they are there overnight are conditions when dark clouds descend in the form of a tail and touch the water surface, which it's locally referred as nsoke, which is water spouts for the audience that is today here. So my case of study, it's trying to analyze a little bit of a water spout case. Possible water spouts case, because we don't have pictures of that. So this is the case overview. This happened in March 28 in 2019. I'm showing here in the left panel the reflectivity and the right panel the radial velocity. And for those who are not familiar on seeing radar images, the reflectivity is mostly representing the intensity of the storm. So warmer colors would be more intense precipitation, and cooler colors, less intense precipitation. And then radial velocity would indicate how this storm is, or the system is moving relative to the radar. You would see that I just highlighted some circles in here, the left and the right panel, and they align. So we see these notches in the reflectivity picture that aligns with these opposite colors in the radial velocity, and that's where presumably water spouts were happening, if they were happening, or that could have happened. So let's go a little bit more in detail in this in these radial velocity images. I cannot say that they're water spouts because we don't have a picture, we don't have a visual on the lake on what was happening that. You can see also it's a case overnight. So I'm just showing here a close-up image of some of these circulations that we see in the previous picture. And for those who are not familiar with radar images, radial velocity, warmer colors would be velocities outbound of the radar, and cooler colors would be inbound towards the radar. So that means that there's probably a circulation happening in that area where we find this opposite or this couplet of velocities. So I'm just going to present some analysis from one circulation for sake of time, but I do have the other, so if somebody wants to ask me later, we can talk about this. So how this case was seen by Titan. So here I'm just showing a two-panel plot. In the upper panel, you could see the major axis of a storm, and the lower panel would be the maximum reflectivity of the storm. And I know that it might be a little bit confusing. There's a lot of things happening here. And what I mostly want to show you is that each dot that it's tracked throughout the time in here, and these lines in different colors represent one single storm within this complex. And remember that one complex will have different storms because they interact, they merge, they split, and they interact with each other. So this main complex that happened to have different circulations was defined as upscale linear around 1 Zulu time and multisail linear around 3 Zulu time. And that's the static image of the storm as an upscale linear at that time and multisail linear at that time. So this is the information that we would get tracking those storms or complexes with Titan, right? And we see this life cycle pretty well defined. We have that the entire system grows and then decays, and the same happens with the reflectivity, which would be the intensity of the storm, like going up and then decaying, so the entire life cycle. So then we tried to check, well, we have these two circulations that are major. Let's see if we can see with other variables from Titan some information in advance of what is happening with that circulation. And in here, again, it's a lot of information. This represents, the upper panel represents the variation of top with time, which basically it's, for those who are not familiar, the change in vertical development. These will represent the variation in volume in time, which it's basically the change in size. Variation in reflectivity in time represents the change in intensity, and the speed, it's basically the propagation speed of the storm. So as you would see from the first and second circulation, there's not actually something that could indicate us like, well, you know, the storm is getting higher, it's getting deeper, like a change in the vertical development before both circulations, or it's changing inside because it's getting more organized before the circulations. We can slightly see that for the first circulation, there's a change or increase in volume that could indicate that the system it's getting into a major stage of organization, but that is not related also to the second circulation. So that couldn't be a pattern that we could focus like, well, every time that the system is getting mature, we'll have a circulation. And with the propagation speed, we can see that for the second circulation, we see that the system is actually increasing in this propagation speed. So probably it's the final stage of this linear system, and also posing a major risk on the lake if it's also propagating with this higher velocity. So since we couldn't see anything or any pattern in advance from these circulations happening, like, indicating that, well, maybe this would show us like there would be some rotation, we went to check the polarimetric radar variables. And for that, I just need to introduce a little bit more of why it's important to have a polarimetric radar. Basically, what we have is the difference between the conventional radar and the dual polarization radar, like having the beam polarized in two different planes. It's how the matter interacts with the phase and the amplitude of the electromagnetic waves. And that is valuable information in the operational arena, especially for nowcasting or for severe storms monitoring, and also in decision-making processes. And since I'm going to show a plot with the ZDR, the differential reflectivity, and I don't want to bore anybody with formulas, I promise this is the only thing that I'm showing here, and it's the ZDR to show that it's basically the relationship and the relation between the polarized reflectivity in the horizontal plane and the vertical plane. So that means that if you have different type of idealized drops, like a small drop would be more rounded and the idealized big drop would be more oblated shape, we would have, for the oblated shape or the bigger drops, we would have more information in the horizontal plane than in the vertical. So we would get then greater values in the reflectivity, in the ZDR maps. With that, there are some features in the operational arena that could be used, which is the ZDR column, which would indicate intensification, the ZDR rings, which could indicate the mid-level maximum vorticity, especially for supercells, and the ZDR arcs, which could indicate low-level rotation along the inflow. So with that said, let's see what we can see with these circulations that we saw first. So this is and again, I'm just showing one circulation for a matter of time, and this is the radial velocity of that circulation, the circulation that we can see at 120 Zulu time. But before that, what we can see is that these inbound velocities impinging in the main system, so like low-level flow in the opposite direction of the main system, which actually create this inflow notch at 0050 Zulu time, and finally this notch is organized in this circulation at 120 Zulu time. How do we see that with the ZDR values, and can we get some further information before this actually happens? Well, with these I'm showing the same times. And what we see is that once these inbound velocities happen, so this low-level flow it's impinging in this system, we see that there is a ZDR enhancement area, and that's probably because the flow is actually pushing downstream the smaller drops, but then the bigger drops are in the forward flank, and then we see these intensified ZDR values. Then we see also that at 0050 time, there appears this tiny arc here, which could be the ZDR arc, indicating that there could be this low-level rotation. So we have information of some rotation happening before actually we could see it in the radial velocity field. And finally, this is matching or aligning with the circulation that we saw in the radial velocity in the ZDR. So we get better, far information, of course, to analyze, and it needs a forecaster actually to be trained and to get to know what is happening in those images. But we can get, with polarimetric radars, we get far information and enhanced information of severe weather threats or dynamics inside storms, and in advance than actually when it's happening. So with that, I just arrived to the summary of this talk. So first, we've demonstrated that Titan is a good real-time tool for real-time monitoring of convection over the lake. It's important to state that because it's an open source tool. Everybody can use it, but also it's already installed in their system. So we should present these results and engage with them so they can use the Titan and you properly monitor storms over the lake. So this is a good tool for them to use and to forecast severe weather on the lake. We've also shown that there's differences in pre-convective environments based on sectors, seasons, and the type of organization. So this information could be used to refine the daily forecasts. And more special, there's the 2025 early warning vision, like kind of follow-up project for this highway project. So hopefully they put more upper air sandings, especially one closer to the radars, and we can get better information and not just rely on models or ERA 5 reanalysis. And then we've shown that dual pole capabilities from the Mwanza radar allow for better understanding of severe convection over Lake Victoria. So that could also be introduced like ZDR column identification or arcs identification automatically into a system like a radar-based system like Titan, and then enhance the operations in the offices. However, there are a lot of questions to be solved, and this is a really cool project, and we have really cool data, but let's touch ground and think on how do we make this classification valuable for the forecasters in Lake Victoria, or also how is this information going to be used in this operational nowcasting effort. We've seen that there's need for additional radar calibration. We've seen some artifacts and things happening in the data, so there's a need also to enhance this, the radar operations there and the calibration. There's also a need on Titan training, for forecasters at the Met Service there. Also a need of dual pole signatures training for different cases, because they do have this information, but they don't use it because they don't know how to use it, the information. And then most important is like who is going to benefit from this new information, who is our main target for all this. So hopefully we can give some solution to these questions, because we just put up there a call for a proposal, and we should see if that moves forward or not. So if this is awarded, then we could have further funding to extend these efforts and then actually go there, train, talk to them, and do this joint effort towards a better nowcasting and early warning system for Lake Victoria and Africa. And well, with that, that's all. Thank you very much for for listening. And if there's any questions, yeah, Sarah, I think that you're gonna get the questions done. Thank you.
Thank you. I will kick off real quick by saying that is an impressive synthesis of a lot of different data. Very nicely done.
Thank you.
So a reminder, if you're online, please submit your questions on Slido. And do we have any questions in the room?
Hi, Anna. Great talk. Very impressive work. I'm wondering if you've looked at how the West African monsoon relates to what's going on in Lake Victoria, because I think that in addition to looking at the smaller scale land breeze, sea breeze interactions, the WAM might be giving you that background state. For example, in March, you saw some similarities across the southern flow. It could be related to the monsoon, and it could help you identify those different characteristics of the different modes. And I'm thinking that going a little bit further with that, locals, I mean, across all Africa, they're all familiar with the monsoon. So in relating that to what's going on in Lake Victoria might help the locals and the forecasters in the area kind of like relate that to what's going on in their climate, right? So something to think about. I don't know. Thank you.
No, we haven't think about it. I thought it was more of a Western African side, but you've been there now. You have also this experience with the locals. So yeah, thank you for that suggestion. It's worth checking in. Thank you.
Looks like we do have a question online. Josh asks, are people really out boating after midnight on the lake? Seems like the worst storms are after midnight, according to your analysis.
Yes, they actually, so the thing is like, yeah, the fishermen go to fish overnight, and that's actually, so the storms are happening, but that does not prevent them from going out there. There's like their way of living, and they're locals, they are aware of and familiar of the weather. So now with the outcomes from the highway, now they know when to like postpone a little bit their operations, but they keep doing that on the lake. It's you know, it's like the storm is not happening in the entire lake. So I guess that if I was a fisherman, I would go out there and fish and say like, well, if a storm is happening, I will have enough time to react. But unfortunately, when they're like really severe, then these waves are higher, and then the accidents happen too. But yeah, they go at night and they fish. Yes. So that's the main purpose of this project, is like to get actually better information for them to make the decision on whether to go or not.
Looks like we have another question from online. Danielle asks, perhaps a bit peripheral to your work, if most of the severe weather is nocturnal, how does this align with the timing of accidents on the lake? And is there an understanding of which sectors of the lake the accidents occur in? Thank you for a very interesting talk.
Yeah, that's a good question, and that is challenging. So I just did a tiny search analysis of that some months ago, and I actually like went to check how many accidents were happening. And first, we don't have reports of if that is happening or not in the entire lake. So there were more accidents reported, especially for the northeastern side of the lake, because of mostly Kenya is reporting those accidents because they have the maritime police, let's say, on the lake. So they report because there's also smugglers, there's other things happening. So it's like a coincidence also that, you know, there's this accident happening because of also other reasons. They overload the vessels and everything, but they also link it to the weather. So we don't have a lot of accidents reports. We don't actually have visuals, pictures, or like anything that says like, oh, this severe weather is happening on the lake. Because also when the fishermen or the communities go there, they probably don't take the phone because they might have just one good phone and they don't want to lose it and they're going there to work. So it's a little bit challenging on getting that information. And also, yeah, I kind of like tried to relate the sectors and the weather with the accidents, and then I saw that I had more accidents in some of the sectors and nothing in Tanzania or southwestern coast, and that's probably because of lack of reporting in the others instead of that. And it's more of a coincidence that the reportings were done in other sectors. So it's challenging. So yeah, hopefully I can go deeper in that realm and see if we can find more accident reporting, but it's a challenge to actually match both. So that would be great also if we can just tackle these questions in further project of this, like the following up for this project.
So what's the state of the affairs right now? Is there a forecast that does come out? And at what time does that forecast come out? Because they go out fishing at night. I don't know if that's night before midnight or night after midnight, but the forecast would have to kind of be timed for their departure. First of all, is there a forecast? Do people listen to those forecasts? Does it make any difference to them? And how do they, with their local knowledge, they're probably pretty familiar with their own environment, what drives their decisions at this point?
So the thing is, like, from highway, one of the major outcomes I explained here before is these forecast charts that are in the 4 time slots, and that's released twice a day. So for that, this information is the one taken to the radio stations, and the radio stations are the one disseminating in local languages to the communities. So that's the chain, and then that happens 2 times a day. The problem is that we're doing these efforts, and also Jim, Rita, where they're training in the past and just like showing them how to properly identify storms or severe threats in storms, because there's a need for nowcast, and especially for the forecasters. Don't think that we can tackle our end user as the fisherman, because there's a lot of steps going on in this chain, and also there's a lot of different language, a lot of social different environments. So what we think is like, well, we have to get better information, better nowcasting products, better to help actually the forecasters who are going to release that, and if they can monitor the weather in real time, which is something that they're not doing now, and they can be updating these forecasts. That's also information that, like early warning system, right? Take action because there's a storm happening in the lake. What I know also is that they also release information through WhatsApp. They have a WhatsApp group for fishermen, so they sometimes release information through WhatsApp. There's screenshots of radar images from forecasters from different offices saying like, well, now these sectors are experiencing probably heavy rain and severe wind, so if you have to operate in that sector, just change operations, etc. But that's how, more or less, now it's happening, everything.
Very nice talk, thank you. So we did a paper almost 15 years ago using TRIM data to look at the intensity of storms around different parts of the tropics, and Africa is somewhere obviously that stands out. Do you notice that when you see a lot of the severe weather signals that you see, do you see very tall convective echoes in your ground-based radar data, or is it more shallow, kind of more mid-latitude type storms?
It's not that high as in Argentina, that I think, with the analysis that I've done, but there is definitely deep convection happening on the lake. Yeah. So there's actually something that I checked before with these convective modes that we define, is that some of them are deeper than others, but then So the deeper probably don't propagate as fast as the shallow ones, and then the shallow ones are the faster in propagated. So the thread in the wind, like related to the wind on the lake, could be happening because of deconvection also, because they're like fast moving, propagating systems. And then we don't have, the problem also is that we try to relate that with altimetry, and we don't have data because we don't have buoys there. So probably in the future efforts, there's going to be more data also to analyze. But that's also like nice to check with the
One other
deconvection.
follow-up. With those values of helicity, one might expect there to be supercell thunderstorms. Do you see those?
I don't think it's a pattern to see like commonly there, but that now I'm starting to get deeper into some severe cases that we have encountered. So I'll tell you. Get further information.
Okay. Any other questions in the room?
Yeah, Anna, do you see any ability to forecast today is going to be a bigger day than another day? Can you tell? Is there any way to tell if it's going to be a big day?
I mean, now we have this pre-convective environment analysis too. If we get data also from the TA4 model, and we can get deeper into that, and we can actually classify or relate these modes with this higher resolution information, maybe we can have like key patterns of, oh wow, this has the proper ingredients to probably become into an upscale growth system, and then like posing risk on the lake. Yeah.
Looks like we have one more question from online. Josh asks, was asking, does your ZDR analysis indicate whether hail is a large threat with these lake storms, or is it mainly just wind threats?
I've just done the analysis for this, for 2 cases now, and it's mostly wind related, although we know also for the highlands, Kenyan highlands, also the northern shore, they are having also severe hailstorms. So probably we can actually check the radar data from Entebbe, and then we'll see further signatures for that. So yeah, more research to do. There's a lot of things now to do.
Yeah, lots to do.
Yes.
Well, we will let you get to it, but let's thank her one more time for a fascinating talk.